Good morning, everyone. Today we will discuss some basic concepts and revise some basic concepts of power system dynamics by solving some important numericals. Now consider this problem when a motor is receiving 25% of the power that is capable of receiving from the infinite bus. When the load on the motor is doubled, calculate the maximum value of delta during the swinging of the rotor around its new equilibrium. So it is a very common problem and it is asked in the university examination also. Let us solve it. So for solving such problem, we need to focus on this delta. So this delta, if I draw the variation of delta with respect to the received power, that how I will make this power angle curve. So power angle curve is nothing but the curve between power output and the load angle. So this is delta, and we know that the electrical power output is nothing but the sinusoidal function of this. So this is the first step to do such kind of exercise. You draw the power angle curve. So likewise, we mark the maximum power which can be transferred. This is Pm, and we can write the expression Pe is equal to Pm sin delta. So when this delta is 90 degree, I can say the maximum power can be transferred, and this will be equal to Pm. So here it is given that initially motor is operating on 25% of this. So that means it will be operating on this 0.25. So this is 0.25 Pm. Corresponding to this 0.25, we will be having one angle which is delta naught. Let us say it is the initial angle delta naught. Now if I just put so this is a point A. So point A is what? Point A is nothing but initial operating equilibrium. So this operating equilibrium is like this. Now if I put the value of these coordinates of point A 0.25 Pm into this expression, suppose this is the expression 1. So by putting the coordinates of A in equation 1, I will get this 0.25 Pm is equal to 0.25 Pm is equal to Pm sin delta. So from here I can easily calculate delta naught, and this delta naught will be equal to sin inverse 0.25. So you just make a thing very appropriate that okay, let us see that this value will be 14.48 degrees. Although it is always advisable to calculate the values in radian, but here we are calculating in degree also. Now here I can also sense that the critical maybe the clearing is equal to at 0. Let me say this delta C is here, and this is corresponding to this delta C. What I can say, the load is actually half. So this 0.5 Pm is equal to Pm sin delta C. So this delta C will come out to be 0.5, or maybe I can say it is equal to sin inverse 0.5, and it is come out to be 30 degrees. So let us see, let us draw it again. So if I draw it again, what I can have from here, I can easily interpret the things. I will be having two angles, and I will be let us observe the rotor swing. So if I observe the rotor swing, let me say this is let me draw it again. So small constructional steps you need to be very careful. So let us draw like this is a power angle curve. So this is the delta, this is the P. Here there is delta naught, and this is suppose this is delta C. So there will be area delta C, and suppose this particular part the rotor swings up to delta m by doubling the load. If I am doubling the load, it is swinging like this. So what we are having over here, this is A, this is B, this is C, this is D, and this is E. Now, as we know that as per equal area criteria, the energy governed by or energy lost by this area ABC will be equal to area CD, and all these point A, B, C, D all the stable indicates the stable region. So what we do by applying, you had to write by applying equal area criteria. This angle, this area ABC will be equal to area BDE. So if I write the expression for area ABC, so it will be equal to, if you see over here, this is 0.5 pm, this is 0.25 pm. So this is 0.5 pm. So this will be the area ABC will be the area of this rectangle, and if I integrate this area between delta naught to delta C, and if I subtract this with this rectangle, I will be getting this area ABC. So I can easily write the expression for this. So it will be equal to 0.5 pm into delta C minus delta naught. So this will be the area of this triangle. So this is this rectangle. So this is the area of OMBC. Now if I calculate the area ACOM, I can easily calculate it will be between delta naught, delta C, and the area under the curve. So the area under the curve will be PM sine delta and D delta, like this. So the area corresponding to ABC, the area ABC will be equal to what? This will be equal to 0.5 pm delta C minus delta naught minus delta naught by delta C pm sine delta and D delta. Likewise, I can also calculate it. Area BD. So let me calculate. So this is expression 2. Now expression 3 represents the area of the area CDE. So this area CDE, how I will calculate? First I will calculate this area under the curve. So this is delta C, delta M, and PM sine delta. D delta will be the area of CE and MN. So this area CEMN. Now from here, if I just reduce this area under the curve of this rectangle CDMN, so area CDMN, what will be this? So this will be equal to 0.5 pm into delta M minus delta C. So final expression I can write delta C, delta M, PM sine delta, D delta minus 0.5 pm delta M minus delta C. So this will be equation 2 and 3. So when I put equation 2 and 3 equal, pm get cancelled, and we are already having the value of delta C, delta naught, and what we need to do? We need to calculate the value of delta M. So from my calculation, I can easily calculate the value of delta M will be around 45 degree. So it will be around 45 degrees. So one trick is here. Whenever you are trying to solve these questions, so these questions, the initial operating point is, so from here I can say initial operating point is this 14.48. Now the delta C is 30 degree, and now further when you calculate, the answer is 45 degree. So always remember that delta naught, delta C and delta M. So there will be an monotonically increase in these angles when you are solving such problem. So this is how we can solve this problem. Now, very important part of dynamic stability is to find out the critical parameters of the circuit breaker. So, in this illustration, I will demonstrate how we can find the value of the critical clearing angle. So, in first part, we divide whole system into three parts. First, let me say that the first equation, that means the pre-fault condition. For pre-fault condition, let me say there will be the value of the active power related with the generator is Pm sin delta. Now, during fault, this is substantially reduced. So, let me write it R1 Pm sin delta like this. So, this is the expression for during fault, and post fault I can say post fault, let us assume this is equal to R2 Pm sin delta. From here I can easily write that this R2 is greater than R1 and R1 is less than 1. These are the essential conditions associated with it. So, let us draw the power angle curve and let us try to understand what is happening to this. So, if I draw the power angle curve, so initially we need to draw the basic pre-fault curve. That means initially there is no fault condition in this. So, this is the basic pre-fault curve. Now, I will draw the during fault curve. So, this during fault curve, the power associated with this is remarkably low. So, from here I can say this is Pm and I can say this is R1 Pm, and likewise I can also I can also deduce one power angle curve for the during fault condition. So, from here I can easily mark that this is the pre-fault curve, this is during fault, and this is post fault. So, let us try to find out the expression for this. Now, when I say the operating line, mechanical operating line, so let me say this is angle delta naught, which is when it is operating, and suppose at delta 1 there is a this is an initial operating equilibrium, and let me say that if fault occur at this point, then the operating point is shifted to the second curve, which is let me say this is the point B. Now, when you see that at point B there is a sufficient difference between the mechanical power. So, this is, let me draw, this is the mechanical power. So, there is a difference between the mechanical power and the electrical output. That means it will correspond to some change in the delta. So, this delta, let me say this is equal to the critical clearing angle. So, this delta is here, and then there will be an operating point. Let me say this is point C, this is point D, and let me say that it is this swing is happened to this delta M. Now, what we are having two areas in it. So, there is one area which corresponds to the gain in the kinetic energy. So, this particular area is represent gain in the kinetic energy, as well as this particular area correspond to the loss in the kinetic energy. So, when we are marking it, so let us keep this point, let me say this is K and this is N. Now, we can apply the equal area. Now, we apply equal area criteria. Now, for equal area criteria, what we need to do? We need to calculate this this area AKBC. So, this area AKBC we need to calculate. Likewise, this area AKBC will be equal to area DKM. if these two area will be equal and the maximum power swing is allowed over here. So, this delta m, let me say this point is delta 1. So, this delta m is obviously equal to pi minus delta 1. Now, beyond this point n, there will be always a position where the operating curve is not actually intersecting with this mechanical power line. So, that means up to this point n, and this point is actually the critical point, that beyond which the mechanical power and electrical power will never be equal. But here up to from A to D to M, these all are the operating point where the electrical power and mechanical power can be compensated. So, beyond this point and the relationship with the delta, I can say that this particular delta is not the value of any delta is not capable to bring that electrical power equal to mechanical power. Now, if I calculate this particular area, so this particular area equal to maybe this triangle, this will be equal this rectangle AK, let me say LO, AKLO minus the area under the curve, which is coming BCLO. So, let me directly write the expression. So, this AK is what? Delta C minus delta naught. So, this will be equal to delta C minus delta naught, and the power will be equal to let me say it is equal to PS initial power, let me say it is equal to PS. Now, what is happening to this particular part is R2 PM sine delta. So, if I calculate this particular area under the curve between this these two, so this will be equal to delta C minus delta 0 R2 PM sine delta. So, this will be equal to delta C R2 PM sine delta, like this. And from here I can write PS is equal to what? PS is equal to PM sine delta naught. So, from here I can easily write delta C minus delta naught PM sine delta naught minus delta naught delta C R2 PM sine delta, like this. Now, from here I can also calculate the second area, which is dkm. So, this dkm is nothing but let me say it is between delta C and delta m, and it is equal to the post fault curve, which is equal to R2 PM sine delta. Just little correction here. We will be writing it for the pre-fault curve. So, it is equal to R1 PM sine delta. So, this is equal to R1 PM sine delta. So, this area of rectangle minus this. So, this is R1 during fault is R1. Now, we calculate this. So, this is R2 PM sine delta, delta m to delta C minus this will be equal to PM, this is equal to PM sine delta naught. The value of this is, and it is multiplied with delta m minus delta C. So, this is expression 1 and this is expression 2. Now, by equating all these equations, I will be able to solve the expression, and it has come out to be cos delta C will be equal to delta m minus delta naught sine delta naught minus R1 cos delta naught plus R2 cos delta m divided by R2 minus R. So, this is a brief introduction to calculate the critical clear angle. So beyond this delta c, there will these two expression will never equal. 1 and 2 will never be equal. So we need to keep this thing in mind while solving the. Now let us take up the problem for solving the critical clearing angle problem, where it says that figure shows a generator connected to an infinite bus through transmission lines. Determine the critical clearing angle for a generator for a three-phase fault at point P. So for this point P, we need to calculate this. Now, for a three-phase fault and point P, when the generator is delivering 1 per unit power, assume that the voltage behind the transient reactance is 1.2 per unit for the generator, and that the voltage at the infinite bus is 1.0. Now, for solving these type of problem, what we need to do? We need to first draw the power angle curve. So, power angle curve can be drawn with the help of calculation of this steady state limit. So, this steady state limit can be calculated by this EG/Vt by x sin delta, EG/Vt by x. Now, this in this particular problem, Eg is given, which is equal to 1.2, Vt is also given, which is equal to 1.0 per unit, and let us calculate this x. So, x is actually a crucial factor. So, let us calculate the power angle curve for the pre-fault conditions. So, in pre-fault condition, there will be no fault. So, in that case, what we need to do? We need to just accumulate all these resistances, inductances. So, this J 0.1, 0.3, J 0.3, that will be equal to all these three are in series. So, this will be equal to J 0.55, and now here also J 0.55 here, and then it is equal to 0.15. So, when I calculate it, when I accumulate all these, I will be able to get. So, this will be equal to 0.45 J plus J 0.55 divided by 2. So, this is come out to be 0.275 J 0.5 plus J 0.25. So, it is coming out to be like J 0.72. So, the value of x will be like this. So, from here pre-fault calculation can be completed. So, this is equal to 1.2, this is equal to 1, and this will be equal to 0.72. From here the PM for the pre-fault condition can be calculated, and it is come out to be 1.67 per unit. So, this result is an important result where we are calculating the steady state capability of the system with reference to no fault. So, in previous slide we have calculated the pre-fault impedance. Now, in this slide we will calculate during fault impedance. So, understand that in these type of problem there will be three levels of reactance. One is pre-fault, second is during, and third one is the post-fault. And in every condition there will be a change in the pre, during and post-fault condition. So, we are having fault over here. So, let us draw the network diagram. So, this is 0.3, which is correspond to generator. Now, the 0.55 is corresponding to the upper transmission line, and the remaining two is actually impedance are corresponding to the transmission line 0.15. So, since fault is here over here, so this 0.25 and 0.15 will be in the series. So, this will be equal to 0.40 per unit. Let me cross J over here. So, this is J, and then this is connected to the motor, which is 0.15 again. Now, what we need to do? We need to calculate the value of the reactance which is connected from this sending end to the receiving end. So, for simplifying this circuit, we need to solve this delta and we need to convert it into the star problem. So, when we need to find when we want to find the connected star element, let me say this star element which is connected to this. So, the connected reactances are 0.5 and 0.55. So, from here this particular element can be written as J 0.15 into 0.55 divided by the summation of this. So, 0.15 plus 0.40 plus 0.55. So, when I calculate it, it will be coming out to be 0.075 per unit. Likewise, if I calculate this, I can easily calculate this will be equal to 0.55 into 0.4 and then it is 0.15 plus 0.4440 plus 0.55 and it is coming out to be this particular part is 0.2. Again we can also calculate this reactance also. So, this is this reactance and now if I calculate this reactance, it will be equal to 0.40 into 0.15 divided by 0.15 plus 0.40 plus 0.55. So, this is coming out to be 0.0545. Now, further we can simplify this network by connecting it. This is delta 0.3. Then we connected 0.075, 0.075 and there will be a reactance which is equal to 0.0545 and then here it is 0.2 and 0.15. So, further if I simplify this network, so this network can be simplified as 0.375, 0.35 and 0.05. So, when I further calculate it, it will be coming out to be 3.133 because I convert this star into delta again. So, this particular part, this particular resistance is calculated. So, this will be equal to what? This will be equal to this multiplied by this upon this will be coming at this multiplied by this, this plus this divided by this multiplied by this divided by this. So, it is coming out to be 3.133. So, this is equal to 0.375 into 0.35 plus 0.35 into 0.05 plus 0.05 into 0.375. All these multiplied and we need to divide it by 0.0545. So, it will be coming out to be 3.133. So, in pre-fault there will be 1.67 per unit. Now, during fault it is coming out to be 3.133 per unit. Now, we need to calculate the post-fault also. Now, let us calculate the post-fault values of the power transfer. So, in post-fault what will be happening? This particular branch is removed. So, total reactance will be because of this generator, this transformer, this transmission line and this motor. So, how we calculate? So, this is equal to 0.3 plus 0.15 plus 0.25 plus 0.15 plus 0.15 like this. So, this will be equal to X will be equal to 1 per unit. So, there is a J always, so J1. So, if I want to calculate the post fault power, the expression will be equal to P is equal to PM sin delta. So, this PM further we can write this Pm, the maximum power which can be transferred, this is equal to EgVT by X. So this Pm can be written as this is 1.2 into 1 divided by 1.2. So this is coming out to be this is 1 per unit, so it is coming out to be Pm will be equal to 1.2. So likewise you need to write the expression for let us see the pre-fault stage. What will be the value? The power angle curve equation can be written as Pe is equal to, let me say, 1.67 sine delta. For during fault condition, this Pe becomes we have calculated and it has reduced 0.383 sine delta, and post fault we have just calculated this will be equal to Pe is equal to 1.2 sine delta. Now these are the representative equations, and corresponding to these equations we can always plot power angle relationship curve. From here I can simply say that pre-fault condition there was power transfer 1.6, then during fault there is a substantial decrement we observe in the power transfer capability of the transmission network. Then this power transfer capability is restored by removing this line. So now we will calculate that the design parameter for the circuit breaker. For this you need to draw the power angle, all these three power angle curves. So let us think one more important observation, that since we are observing change in these power equations, power angle equations, I can say that the pre-fault resistance, reactance, pre-fault reactance and post-fault reactance, both of these reactances are less than during fault. So this is an important observation. That's why the power transfer capability is reduced. Now let us draw all three power angle curves. So let me draw this power angle curve and we will perform the calculations. Let us assume that this is delta and this is the electrical power transferred. So first I will draw the pre-fault curve. So this pre-fault curve is like this. This is I can say it is equal to 1.67. So let me mark it clearly. Now we assume we have calculated that the during fault curve is the curve where there was a substantial decrement in the maximum power. So this is 0. You say 0. This particular equation we have written 0.383. And again, if I want to draw the post fault curve, so this post fault curve I can draw like this. I can always have the mechanical input line, which is this is mechanical input. Now let us do some calculation. If I observe the, so let us draw it a bigger picture so that we can understand what is happening to this, and I will perform the calculations also. So this is how the pre-fault curve looks like. This is how the during fault curve looks like, and this is how post fault curve look like. So mark PE delta over here. I can always mark the mechanical input line, which is 1 per unit, which is given. So this is mechanical input line. So we will perform the calculations now. Very important point. So this point A, let us consider this point is an initial operating point and it corresponds to angle. Let me say this is delta 0. So from pre-fault curve, if I calculate that this point A is having coordinate delta naught and 1. So if I recall the pre-fault curve equation, it is equal to 1.67 sine delta. So I put these in this. So this will be equal to 1 is equal to 1.67 sine delta naught. So this delta naught will be sine inverse 1 by 1.67. So ultimately this delta naught I will be having it is equal to, let me say it is equal to 0.6 in radian. So this delta naught is coming out to be delta naught is equal to 0.642 radians. This is an important observation, we need to remember it. Now, when the fault occurs, this operating point comes up to this point B, and let me say it is having a swing till point C. So this point C correspond to let me say it is a critical clearing angle, which is known as like this, delta CR. Now what is happening to this particular critical clearing angle, that beyond this point let me say this is M, beyond this point N, there will be always a position where the value of electrical power is greater than the mechanical input. That means on these points the value of mechanical power will be greater than electrical power is greater than mechanical power, and if we increase the delta, there will be always possibility that we will reach an we will reach an operating equilibrium where the mechanical input and electrical output lines are intersecting with each other. But here in this case beyond N, if I am increasing the delta, I won't be able to get any operating equilibrium because the mechanical input will be always higher. So this is the critical clearing angle where we need to see. So this is how I mark delta M over here. So this delta M is equal to pi minus delta 1, and this delta 1 is what? This delta 1 is this angle. So always remember there is a relationship, this delta M is greater than this delta CR, it will be greater than delta M, and it will be greater than delta 0. So this is how we do this. Now what we do, we apply equal area criteria. So this equal area criteria I can I can see two areas. Let me highlight these areas. So this will be the area where the electrical output is greater than mechanical, and this will be the area corresponding to the gain in the kinetic energy. So this area, let me say this area AMBC, this area AMBC is what? It corresponds to gain in kinetic energy, and this area MN, hatched area responds to loss in the kinetic energy. So correspondingly, if I draw this point is, so let me say it is K, and this is L, and this is M. Let me say it is Z. Let me write, this is Z. Now what I need to do, I need to calculate this. So this area AMBC, this area MBC, I can calculate this area AMBC will be area of this rectangle. So let me show the rectangle. So this rectangle AKLM minus, if I minus this area BCKL, I will be able to get this area. So this area AMBC is equal to area of AMKL minus area BCKL. So this will be the first area. Now second area, area MN. So this area AMN is, if I calculate this area M, if I calculate this L, let me say this is J. So if I calculate the area L, J and Z, so area L, J and Z, and if I subtract the area of this rectangle, this area rectangle M, N, L, Z, I will be able to find out the two areas, and what I will do, I will equate it. Now let us see how it goes. Now for calculating AMKL area, so this area will be height into length into height, so this will be equal to delta CR minus delta naught into this 1. This is 1 mechanical input PM, and this is equal to 1. So I multiplied it with 1 minus area under the curve between the post fault during fault curve. So this during fault curve will be what? Between delta CR delta naught 0.383 sin delta. So this is area, this corresponds to area AMBC. Likewise, this area MN is also calculated. So what I will do, I will integrate from delta CR to delta M. Now delta M I have to calculate, so I will find the intersection between this two. So this delta 1, actually this point, let me say this is point B. So point B is the new operating equilibrium for this. So at point B, if I apply, the coordinate of point B is delta 1 and 1, and the expression is 1.2 sin delta. So if I put 1 and delta 1 is here, then what I will get, sin delta 1 is equal to 1 by 1.2. So this delta 1 will be coming out as, this delta 1 will be coming out, let me say it is coming out to be 0.8 radian. So this will be coming out to be 0.8 radian. So we calculate delta naught is equal to 0.6. Now delta 1 is 0.8 radian. So I will employ all these values in this. So this is integration between delta CR and delta M. So this delta M is pi minus delta 1. So this delta M will be equal to 3.14 minus 0.8. So it is coming out to be, let me say it is coming out to be 2.3. So this 2.3 is we are having here. So this delta M by delta CR, I will evaluate 1.2 sin delta minus angle of minus this. So this will be equal to delta M minus delta CR into 1, and this corresponds to area MN. So by applying equal area criteria, I can always say that these two areas will be equal. So if I put these two areas equal, then I will be easily getting, so delta naught I am having, delta M I am having, there will be a non-linear relationship between delta and there will be a sinusoidal term, cosine terms are coming in the expression. So what you have to do, what you need to do, you have to guess that it is 0.6, it is 0.8 and it is 2.3. So the value of this delta CR will be in between this in between 2.3 and 0.8. So if you solve it, you will be able to get delta CR.